Hey everyone, in this video we are going to start talking about sequences, specifically arithmetic sequences. And in order to discuss them, we will talk about how to find unknown numbers in a sequence using both explicit and recursive formulas. So I just used a lot of words there, don't worry, I'm going to go and define them. So let's start with what in fact is an arithmetic sequence. And I know it looks like arithmetic, but it's arithmetic. So we've got a few sequences here. A sequence is just a list of numbers. It could also be a list of objects, like a visual pattern, but in this case, they're all numbers. And we're going to talk about which one of these, and only one of them, is in fact arithmetic. So what does that mean? And in order to decide that, I want you to just take a moment and look at each of the sequences and in your head come up with what is the pattern? How are we growing from one step to the next step in each one? Take a moment, I'll come back. Okay, here are the patterns I came up with for each sequence. So the first one, you're multiplying by 2 to get the next one. The next one is interesting. You add 3, and then you add 5, and then you add 7, you add 9. And the last one, you just add a constant 4 each time. And the one that's arithmetic is the last one. And this is the type of sequences we're going to talk about today. In the future, we'll talk about the other ones. So there's all kinds of patterns in sequences. The one we want to look at is the one where you're adding a constant common difference. I'm going to write that down because there's some vocab here. So this guy's an example of arithmetic. It's arithmetic because you're adding, or you could also subtract, which would just be a decreasing sequence. Adding or subtract a constant common difference. Common difference is a vocab word here as well. Let's get to that too. Okay, so arithmetic ones are where you add or subtract a constant common difference. The common difference is the number you're adding or subtracting. So the common difference in this example is 4, because it's the difference between the step numbers. Okay, and I keep using the word step, so let's go ahead and just define that. The step is the position in the sequence. So I'd call this step 1, step 2, step 3, step 4, step 5. The step is just the position in the sequence. I use these words a lot, so it's worth writing them down. Cool. So now that we know what an arithmetic sequence is, we will look at these guys later, but not in this video. Let's just focus on the 3, 7, 11, 15, 19, 1. And the first thing we're going to do is you can look at sequences, just look at patterns, and we can look at this and say, what is the next step? So I know in step 1, 2, 3, 4, 5, what I want to know is step 6. So we know we have 3, 7, 11, 15, 19, and we know that the pattern is adding 4 each time. So if I take 19 and I add 4 to it, I would get 23, and you can find the next step. And I could find step 7 by continuing to do this, and 8 and 9 and 10 and so on and so forth. But what if then I throw you for a loop and ask you to find something like step 43? And you'd be like, really, Miss Mancini, you're going to have me do that 43 times? And my answer would be no, right? In math class, when we have an unknown, we want to find the most efficient way of solving for that unknown. And what do we do when we have an unknown and we want to solve for it? That's where equations come up. There are 2 different types of equations we use in sequences, and they're called explicit formulas or recursive formulas, just both equations to describe sequences. Okay. Sometimes one's easier than the other. That's why we study both. It just depends on what kind of sequence you have. Okay, explicit formula is actually probably what's more familiar to you, but I'm going to start with what a recursive formula is. So the recursive formula is when you essentially describe the sequence in terms of its previous steps. Or I guess it could be previous or next steps. And although this equation might be easier to understand, the notation is what makes this trickier. So I'm going to give you the example for our sequence above. First, I'm going to start by kind of writing in a sentence, and then I'll translate it to a formula. So if I were to describe our above sequence in terms of its previous or next steps, I would say something like, to get the next step, you would take the previous step and add 4. I highly recommend you write this down. And add 4. Okay, verbally, this is exactly what a recursive formula is. There's no notation yet, which I'll get to in a second, but that's all it is you would say to get the next step, you take the previous step and add 4. So now there's a little bit of notation that goes into how to describe that more mathematically. So first and foremost, in sequences, instead of using x's and y's, n is the universal variable for step number. So step 1, you would say n equals 1. Step 2, n is 2, so on and so forth. Okay, a sub n is the universal notation. So that's a sub n. So it's got like a subscript here. That's the universal notation for the number in the step. We really define that as the output of the sequence, or the nth term is the formal definition, which just means what's the number at that step, or let's go, how many at that step. It could be a number, it could be objects. Okay, so for example, let's be even a little bit more specific here. If I had like a sub 2 for my sequence here, n is then 2, right? So it was a sub n, now it's a sub 2. So 2 is the step number. And you would say a sub 2 was, what's the step number at the second step? We'd be here. So at the second step, we would have 7 is my output. So just some notational stuff here. And let's say I did like a sub n plus 1. What that would mean is a sub n is the next term. A and n plus 1, it's like you're taking the step number and adding 1. So this would mean the next term. You're taking the step number, which is n, and adding 1. So that's a way of saying the next term. Or if you have like a sub n minus 1, it'd be like you're taking the step number and removing 1. So that would be the previous term. Honestly, this is the hardest part about recursive formulas, so if you have questions, let me know. Okay, now I'm going to go ahead and translate this sentence into an actual recursive formula. So it says to get the next step, you would take the previous step and add 4, or I guess it should say to get the step that is in question. Okay, so to get the general term, the nth term, you would take the previous step, which would be n minus 1, because it's the step before, and you add 4 to it. And that would be the recursive formula for my sequence. Okay, so again, this is, notation is kind of annoying here, but this is all you're translating. The idea makes sense. To get the step, you take the step before it and you add 4. You could also write this as to get the next step. So you'd take the step number and add 1. You would take the step before it, which would be a sub n, add 4. Either of these would be correct. There's a few different ways to say it. But all the recursive formula does is just kind of relates the sequence to its previous or next step. So in order to use the recursive formula, you have to know at least one of the step numbers. Whereas in the explicit formula, you can actually use this without knowing any number in the sequence. So sometimes it's more useful, but more difficult. Sometimes it's easier, it just depends. So an explicit formula, on the other hand, is probably what's familiar to you. You can compare an explicit formula just to the equation of a function. Okay, we've studied functions a little bit. You know linear functions like y equals mx plus b. That's pretty much what an explicit formula is. So even though we're talking about sequences, not function, that's kind of the idea of what it is. So in an explicit formula, the input is normally x, but is now n. So I'm actually not even going to write x. The input is now n instead of x. N is the step number. So if you plug in the step number to this equation, your output will be how many are in that step. So in this case, your output is still that notation. Instead of y, we use a sub n. So a sub n is kind of like y, and n is kind of like x. So the output, or a sub n, would be how many in that step. Okay, so again, similar at step 1, the output would be 7, same idea here. Okay, and since I said it's kind of like the equation of function, I actually think it's useful to treat the sequence like it's a function to see how it grows, and then that can help us come up with this explicit formula. So this particular sequence we're focusing on today has a constant common difference. It's going up by 4. I'm going to plot this on a coordinate plane so you guys can kind of visualize how that growth is happening here. So here's that sequence. Step 1, you're at 3. I just put it in a table. Step 2, you're at 7. Step 3, you're at 11. Remember I said step number was, it's n, but it's kind of like x, and the output is a sub n, but it's kind of like y. I'm just translating into a function so we can look at something familiar. And you'll see that this function does look linear. If I connect these dots, we would get a line. So an arithmetic sequence is really easily compared to a linear function. Or you can say it's linear in its growth, even though, it's not a function. So that's why I'm saying linear growth. Okay, so anytime you're looking at an arithmetic sequence, you can compare it to a linear equation. And one way we know of writing linear equations is y equals mx plus b. Okay, so that's the function way of writing it. To translate that into sequences, it would be a sub n is like y, and then x is now n, but same idea, right? So you've got a slope. That's how you change over time. You've got a y-intercept. You've got input and output. We just change what the name of the inputs and outputs are. Okay, now looking at this graph here, what is my slope? Let's start there. So my slope is my rate of change, and how I'm changing, rise over run is something we can look at. I'm going up 1, 2, 3, 4 over 1, so my slope is 4. And 4 is how many you're adding as you go up each step. So for every one step, I go up 4 numbers. 1 step, 4 numbers, 1 step, 4 numbers. Because that's constant, that is your slope. Okay, so in this case, my m is 4. So I'm going to start plugging that in. I just need my y-intercept. Okay, and if I look at this graph, you'll notice the y-intercept wasn't necessarily plotted as a point. That's because your y-intercept is where your x value is 0, right? So where is my x value 0 on this graph? So let's plug that in. So we have step 1 at 3. How do I get backwards 1 step? Or the previous step is instead of adding 4, you would have to subtract 4, which would put you at -1. And you can kind of see that that works and follows the pattern here. So typically you don't have negative numbers and 0. We don't have 0 as my step. We usually start at step 1. So to find your y-intercept, you would kind of have to go backwards 1 step and get the 0th step. Doesn't really make sense, but it works for us. So my b is -1. And here's my equation for the sequence. If you plug in any step number for n, you can tell me how many numbers are going to be in the sequence, such as 43. So let's say it's step 43, that's my n. 4 times 43 minus 1, what does that get me? My calculator tells me 171. And why does that make sense? Well, 4 times a step number is going to tell you how many 4s you're adding. So at 43, you've added 43 4s, but you got to subtract 1 to get the actual sequence, since we got to shift back to step 0, essentially. Long story short. Okay, and that's one way to write an explicit formula, and it's nice because you don't have to have the previous steps to be able to use it, whereas in recursive formula, you have to have the previous step. Okay, there's one other way to write an explicit formula, and you have options. Option 1 is to compare to a linear function. Option 2 is the formula for an arithmetic sequence, which goes something like this. To get the general step, you would take the first step, which notation-wise, we would have a sub 1, because 1 is the first step, n is the step number, a1 is the first step. And you would add the common difference n minus 1 times. And I'm going to leave it at that for the video. I just want to introduce you to this formula. Please have it written down, and I'll kind of debrief why that makes sense in our next conversation. You may just want to write down again that a sub 1 would mean step number 1. Okay, so this is the formula for an arithmetic sequence. Although there are many ways to write an arithmetic sequence, we will be talking about this one a lot more in the coming days. Okay, if you have any questions, please make sure you ask them. Otherwise, thanks for listening about arithmetic sequences.